Good morning, future presidents. You have a midterm next week. Yes. Okay, so your midterm is in class 1 week from today. Oh, I forgot to put in there. It covers chapters 1 through 3, including stuff that we covered in lecture. Anything we covered in lecture or anything that was in the chapters is fair game to be on the midterm. It will be in class. Let's see, a few announcements. There will be seating assignments in class for the exam, so those will be posted probably over the weekend. If you're left-handed and you want a left-handed desk, there's a handful of left-handed desks along this row. Please contact the head GSI as soon as possible, probably by today, and you'll get assigned to one of those. There's not very many of those in this class, unfortunately, in this classroom, but there are a few of them. DSP students, we are making accommodations for you guys. You'll probably be taking the exam somewhere else. I know you're going to be taking it somewhere else. You guys will get a personal message through BSpace or in your email, probably by the end of the week. So don't worry about that. If you've been anticipating that, we are on top of that. So if you're going to be away at a sporting event, I've had a number of you contact me. Thank you for contacting me well in advance. I probably lost your emails by now, so this is the right time to contact me again about that. So especially have your coaches contact me, and we can arrange for you guys to take the exams while you guys are away. There will be a review this weekend. I don't think we have a final room and time for that, but I'm anticipating that will be probably Saturday afternoon sometime. Is that what we were shooting for? Okay, so you guys will get a message by that on BSpace about that before the end of the week. So, and during that review, they'll probably be going over the practice midterm and discussing the answers for that. So if you have any questions about the practice midterm or anything you didn't understand, that's a good time to come. So for the exam, we'll give you the exam. You don't need a blue book for that. It's closed book, no notes. So it's just you and the exam and your creation and your pen. Okay, and of course no calculators. There isn't any math on the exam. So any questions? Yeah, probably a comment. Huh? Oh, that's right, thanks. So we will be doing some ID spot checks, so please have your student IDs when you show up for the exam. Thanks, yeah. That's a great question. The question is, will the review session be webcasted? I do not think so. That kind of depends on what room we have, but I seriously doubt it. So, but if you really want that, you might send the head GSI a message about that, but I would not anticipate that. That's kind of hard to arrange on the weekends, I think. So, yeah, man.
Probably not because you need aging staff.
Yeah, exactly. Probably not because there's actually staff that does that. And I doubt we can get them to work on the weekends, so I wouldn't anticipate that. So, okay, any other questions? No. Okay, so today we are starting on chapter 4. So material today is not going to be on this midterm. It'll be on the next one. We are kind of wrapping up our study of classical mechanics. We're going to be moving on to other topics in physics. Today is one of our last days of classical mechanics. I'm doing a little bit, I'm condensing some of the material in sections 4.1, and 4.2 today. The lecture on Thursday is going to be completely on special relativity, so we're going to be talking a lot about Einstein's theory of relativity on Thursday. I do know that it is Rosh Hashanah, and some of you guys won't be here on Thursday. So A, there won't be a quiz on Thursday. And B, it will be webcast, so you guys can catch up on those lectures if you want. And otherwise, Happy New Year. You're welcome. Okay, so let's start by talking about gyroscopes and precession. This is one of those really high-level topics in classical mechanics, which a lot of people just turn their brains off when we start talking about gyroscopes and precession. But it's really easy. So let's understand the idea of gyroscopes. A gyroscope is really just a spinning top. Okay. And often gyroscopes are pictured in what we call a gimbal. Okay, gimbals. Okay, gimbals allow them to rotate without feeling any torque. Okay, so I could draw a really bad picture of that, or I can just show you what I'm talking about. So here is a gyroscope. Okay, it's just a rotating top. It is mounted in two sets of gimbals, just like Lady Gaga. Okay, so free to rotate in this direction. Okay, free to rotate in that direction. Okay, so the thing about that rotation is that it doesn't apply any torque on the, well, if it's perfect, it doesn't apply any torque on this. So it's a torque-free system. Okay, so if we get that spinning up, let's get that rotating, because it's much more interesting when it's rotating. Okay, we're just spinning this up just like we spun up the top on the table before. Okay, so I am giving this gyroscope quite a bit of angular momentum. Let me get it going really good here. There we go. Okay, so I've given this quite a bit of angular momentum. Let me put it in a slightly different orientation here. Okay, so this thing is spinning. Okay, it's got a really high angular velocity. Okay, it's spinning in this direction, so it's got an angular momentum pointed in that direction. Remember our right-hand rule around the direction of curve. Okay, so now the thing about that gimbals is it doesn't put any torque in that. So I'm going to walk around with this a little bit. You might need to pan out some. Okay, so angular momentum is conserved. Angular momentum is pointing off in that direction, which means that I can basically walk wherever I want with this, and it's always going to stay pointing in the same direction, okay? Because its angular momentum is conserved, and the gimbals are not exerting any torque on it, okay? So angular momentum is always pointing off in that direction, okay? I could try to rotate it however I want, okay? But the angular momentum is always conserved. Okay, gyroscope measures direction. It's a very, very precise way of measuring directional information because when angular momentum is conserved, the gyroscope will stay pointing in the same direction. So these are used quite a bit in what we call inertial navigation systems. These were used a little bit more before GPS systems became quite so common, but they're still used because they are even more precise. Okay. Inertial navigation systems, they basically mount a gyroscope like this in gimbals, a lot fancier gimbals than we've got here in terms of their reduced friction, usually in a vacuum, so there's no air resistance either. Okay. And then you get them spinning up, and they always point in the same direction. very convenient if you're trying to go places. It's like a compass that always points to the north. Okay, so it's very good for navigation systems that are used. It's often used in, well, the place where you need really precise navigation are intercontinental ballistic missiles. Okay, so those have these inertial systems in them. But they're also used in airplanes and ships. They're used in mining equipment that goes down below the ground. So you can get the magnetic directions pretty messed up down there, and you don't have access to GPS. But you can still do very precise gyroscopic navigation. Okay, so that is when the gyroscope is mounted in these gimbals. Okay, so you can see that the gimbals are basically holding the gyroscope on the two ends. Okay? Remember, the weight of the gyroscope is acting as if it's in the middle, so it's right in the middle of the rotation, so that means that it's never getting a torque exerted on it. Okay? So things get a little bit more interesting if we let torques come in to the system. So let's start looking at this gyroscope. So here's another gyroscope I'm going to start rotating up. Okay. You can see it's not mounted in the gimbal system. And right now I've got it, this is its rotation axis here. So it is free to rotate around this axis. Right now I have it balanced, so the weight of the gyroscope is being counterbalanced by this mass over here. But I can change that. I can adjust this. So if I move that all the way over there, there's definitely a torque acting on this. There's a lever arm acting around this point. Okay. There's a center of gravity in the middle of the gyroscope. So a lever arm and a weight produces a torque. Okay. If I move this mass back, so there is where the torques are balanced, more or less, roughly. Okay, but I can keep on moving this even further, right? And I can change the direction of the torque on this. So there's a torque down in this direction, pointing in that direction. Okay, so let me balance this out while I spin it up. Otherwise, it's going to be hard to spin. That's probably pretty good. Let's get this thing rotating, give it some angular momentum. Turn that around there. Hear that one spinning out, right? Okay, that's probably about as fast as I can get that going. Okay, so this thing now has angular momentum. It's pointed in your direction, towards the audience. Okay? I've got the torques on this balance so that it's not moving anywhere. Okay? But let me move this mass so we get a little bit of torque on this system now. And let's see what happens to this. So a little bit of torque on this system is starting the angular momentum to start rotating around in a circle. Now let's think about the torque acting on this, though. The torque is acting, so there is the rotation axis. There is the lever arm. There is the weight of this moving downwards. So you think that the torque is trying to move it down. Makes it want to fall, right? Before I had the angular momentum on there. But it's not. It's just making it rotate. I'll do this even more dramatically, so there's a bigger torque on that. Okay. It's just moving around in a circle. So we call this motion precession. That's when the angular momentum is changing its direction. Let me speed this back up. Okay, so putting a little torque on there starts the angular momentum moving in a circle, but not in the direction you might have anticipated. Now let me swap this so that the torque is acting in the opposite direction. I got it going a little bit down. Oops, see, my intuition is backfiring here. I keep wanting to lift it up, and that's the wrong thing I should be doing. There we go. Okay, the torque is making the angular momentum precess, okay, but not in the direction that we might expect. Let's draw a picture of this and try to explain it, and then I'll show you a couple more examples of that. Okay, it's going to be making a lot of noise. Okay, so let's draw a picture of that. Here is our axis for that top. Here is the top itself, or the gyroscope. Okay, so I'm trying to draw this a little bit 3D. Okay, so there is that is a really bad top, isn't it? Let me redraw that. Oh my Lord. Not the quality you paid for, is it? Okay, there we go. So there is the mass of our top. Okay, here is its rotation axis. Okay, so that mass, that top has a mass. It's got a weight. It's being supported. Let's draw that as a little point there, which is supporting that. Okay, so let's draw through a couple of things on here. So there's our gyroscope. It's got a mass, and it has a rotational mass. When it's rotating, it's got a weight, which is acting at the center of mass, which is pulling it downwards. It has a lever arm here. It's being supported at this end. So there is the lever arm. This is the point of support. Okay. So that's also the rotation axis for the torque. Okay, so that is this point right here. Okay. So it's the point where this can pivot around. Okay, so here's our lever arm exerting from this point. It's got a weight that's acting downwards. Okay, so it's got a torque that's acting into the board. Okay, so let's draw this thing as spinning. So let's say it's spinning around in this direction. Okay, so if it's spinning around like that, it's got an angular momentum. Okay, that is off to the right. Okay, now let's draw that from above so we can draw the torque on there. Okay, so this is the view from us looking down from above, down on here. Okay, so if we're looking down on there, we've got the angular momentum still pointing off to the right. Okay, but let's look at the torque up there. We've got a lever arm that's going off to the right. We've got the weight that is going downwards. Okay, so that means in the top picture, the torque is acting into the board. Okay, in this picture from above, so now we're looking from above, that means the torque is acting perpendicular to the angular momentum. Okay, this looks an awful lot like the situation that we had in the last lecture with centripetal forces, right? Where the force or the acceleration was perpendicular to the velocity. Okay? So we're going to talk about that more. Okay? But let's think about that. Here is our lever arm, and there is the weight. The torque is wanting to act to make that drop in this direction. Okay? But that is only true if it doesn't have any angular momentum. Remember, torque is the change in angular momentum of the system, just like a force is creating acceleration, which is the rate change of the velocity of the system. So a torque is trying to change an angular momentum that's already there. If the system doesn't have any angular momentum, then it's just going to rotate it down and make it drop. Okay? But if it does have angular momentum, like the system does when we spin it up, then you've got to look at how the torque is affecting the existing angular momentum, not how it would make it move if it didn't have any angular momentum. So let's draw the exact same picture we drew last time for velocities and accelerations, but this time let's think of them in terms of angular velocities and angular accelerations. So this is our angular velocity. We're going to draw that pointing upwards. It would also be the direction of our angular momentum for this system when you include the rotational mass. Now let's think about the direction of the torque and the angular acceleration. Okay? So if we've got an angular acceleration that is acting in that direction, or a torque that's acting in that direction, creating an angular acceleration, okay? That angular acceleration is directed along the same direction as the angular velocity. So that's going to make it spin faster. But it's going to keep it in the same direction. Okay. Likewise, if we've got an angular acceleration that is directed opposite, so we have a torque that is in the opposite direction from the existing angular momentum, that's going to make it spin slower. But it's not going to affect the direction unless it makes it spin slow enough that it flips. Okay? But that's really just negative, so that's a positive negative thing. It's not actually turning the direction. Okay, so that's if the accelerations are along or against or directly against the direction of the initial velocity. Now, if it's perpendicular, this is just like a centripetal force. Okay? A torque that is perpendicular to the angular velocity, or to the angular momentum, is acting to change the direction of this velocity, but it's not acting to change the magnitude. Okay, so this will change the direction of the rotation, but not the spin rate. Okay? So that is if there is an existing angular velocity, and likewise in this direction it would change to the opposite direction, so it's going to turn the rotation axis to the left, but it won't affect the spin rate. Okay, so let's go back and look at this again. I'm going to balance it so we can actually put whatever torque we want on this system. Okay, almost got it. It shouldn't be that hard. There we go. Okay, so this right now is balanced, so there's no net torque on this system. So we can do the torques whatever direction we want. Okay. Once again, doesn't have any angular velocity, no angular momentum. If I push down on this side, it's just going to make it fall. If I push down this side, it's going to make it fall, so pretty obvious. Okay. Let me go ahead and give it some angular momentum. Okay, that's probably good. Okay, so once again, this is balance. It's got a constant angular momentum. Now I'm going to provide a torque. So here's my lever arm. There's my direction. I'm going to push down on it. Okay, if I push down on this side, it makes it move to the right. Actually, there we go. Let me push harder. So I'm pushing downwards. I am not rotating this in a circle. Okay. Likewise, if I push up on it, it's going to go back in the opposite direction. Okay. It's because the torque is acting perpendicular to the direction of angular momentum. If I push to the side, let's think about that. So here is the angular momentum. I'm going to push. Here is the moment arm. I'm going to push to the side, so the torque is upwards. So if I push to the side, it just moves it down. If I push on the other side, it moves it up. Okay? This is because the torque I'm exerting on this is affecting the existing angular momentum of the system. So it's not acting like we would intuitively think it would act if the system wasn't spinning. But once you know it has angular momentum and the torque is the change in the angular momentum, then this becomes much more intuitively obvious, I think, why it's moving like this. Okay? Okay, now, one more thing which often confuses students, confuses me sometimes. Okay, let me give this let me spin it up one more time. Okay, so it's got angular momentum directed along the axis. I've moved this mass, so it's got a net torque on it, so it's going to start spinning. Okay, so we call this spinning motion precession. It's precession because it's changing the direction of angular momentum. Now, the part that confuses people is that now it looks like it's spinning around this direction, right? So you might think it's picked up angular momentum along this axis, okay, as well. But that is not angular momentum. And the reason is that it's only spinning around this direction because it's got a torque exerted on it. Okay? And if we balance that torque, then the precession goes away. Okay? So that rotation of the spin axis, which we call precession, is not a new form of angular momentum. Okay? It's because it only exists when the torque is acting on the system. It is not angular momentum in and of itself. That motion, forcing the angular momentum to change its direction, will stop as soon as the torques stop on the system, which happens when I push down on it to balance the torques on there. Okay? So precession is the change in direction of the angular momentum because the torque is acting on the system. It's acting perpendicular to the direction of the angular momentum, okay, which makes it look exactly like uniform circular motion, which we saw last time. Okay. But the precession itself is not introducing angular momentum into the system. Okay. So that is gyroscopes and precession. Okay. This was introduced in your book, by the way, in terms of bicycles, right? They were talking about how when these things are spinning up, oops, doesn't sound good, does it? When these are spinning up, because the angular momentum wants to be conserved, like in your bike tires when they're spinning, that it adds a lot of stability to the system. And they call it dynamic stability because you get that when you're actually moving, when the bike is rolling because the wheels are spinning and they have angular momentum, which doesn't want to change direction. So it adds stability to the bike. Okay, let's see. Is there any questions about the precession? No. Easy, huh? I told you it was easy. Gyroscopes are easy. Yeah? Okay, let's talk a little bit about rockets then. So, kind of a hodgepodge of different topics in this chapter. Like I said, they're sort of like the last few items from classical mechanics that we're sort of taking the rest of the survey of classical mechanics and putting it into one chapter. Okay, rocket propulsion. This is another topic which, now that you've got a pretty good understanding of Newton's three laws, is probably pretty easy to understand. But there are a lot of misconceptions about rocket motion. So we'll talk a little bit about what's going on, and then we'll talk about the misconceptions. And so you can decide whether you still have those or not. I'm guessing most of you are already past that point. So rockets. A rocket expels usually a gas. So it expels its fuel, which is usually a gas, at a fixed speed. Which we usually call the exhaust speed. Okay, from its thrusters. In order to accelerate. Okay, pretty intuitive. Rockets are expelling gas out the thruster end in order to accelerate forward. Okay? So let's do a very simple model of a rocket. Let's try to understand the basic idea here. Okay, so let's imagine, instead of a conventional rocket, let's imagine that you are riding on a rocket ship, and you have this big stack of baseballs that you are free to throw out the back end of the rocket. Okay? So here you are riding. Let's going to start at rest. So the velocity of the rocket's equal to 0, and let's imagine you're out here in space somewhere, just sitting there. The rocket has some mass. Okay, that includes you and all the baseballs that are on there. Okay? And each one of these little baseballs has a mass. Let's call it little m for the mass of the baseball. Okay, so that is going to be the starting position. Now let's just imagine that you are going to take up one of those baseballs and throw it out the back of that rocket ship. Okay, so you're going to impart it with some exhaust speed, okay, out the back. So let's draw that situation once you have thrown that out. Okay, here is, once again, the rocket ship with you. There are all those baseballs minus 1, because now you have got one of those baseballs. Remember, it's got a mass m, and it has been thrown off to the left direction with some exhaust speed. That's how fast you can throw it out the back of the rocket. Now, you have imparted a momentum to that ball going off to the left side, which we know from Newton's third law means that there was an action-reaction force. Okay? Momentum, in order to be conserved, means that the rocket and the system has to be moving off to the right to conserve linear momentum. And there's another piece here, though, because now the rocket is not the same mass, because we have thrown this baseball out the back. So the new mass of the rocket is the original mass minus the amount of mass that you threw out the back. Okay. Now, we also know two things. So we know, one, that the mass of the spacecraft has decreased. okay, because we threw that mass out the back. And the second is that the rocket has picked up a velocity to conserve angular momentum. Sorry, not angular momentum, linear momentum, linear momentum. Okay, so how much velocity is it picked up? Well, that is pretty easy to derive, because we know how much momentum that baseball has. Initially, the entire system had 0 momentum. Okay? So now, after you've thrown that, the momentum of this ball going off to the left has to equal the momentum of the system going off to the right. So that just means the mass of the baseball times the exhaust speed, how fast you could throw it, has to be equal to now the mass of the rocket minus that mass that you threw off, okay, times the speed that the rocket's moving off to the right. So that's just conservation of linear momentum for that system. Okay, success. You've got that rocket moving. Okay? The fact that you threw that baseball out the back in order to conserve angular momentum means the rocket has to move off to the right. Okay, so that thing works like success. So in order to speed that rocket up, now you're just going to start throwing baseballs out as fast as you can, right, to get that rocket speeded up. So you're going to have a rate at which you're throwing those out. Okay, so now you're going to start throwing the baseballs. So we're going to start throwing them out at a fixed rate. Okay, so, and that's going to be creating a constant thrust or constant acceleration, pushing that off to the right. So thrust is just the term we use for force in a rocket ship. Okay. So when you start throwing those baseballs out the back, it's going to exert a force on the ship, moving it off to the right, so creating a constant acceleration. Okay, so let's write that down in terms of the equation for thrust. So intuitively we know that, okay, so you're throwing those baseballs out at a fixed speed, the exhaust speed. So each one you throw out is going to give the rocket ship a fixed amount of momentum going off to the right. Okay? So the only way you can increase the amount of force is if you can throw them out faster and faster. So the faster you can throw them out the back, right, the more that you're going to accelerate off to the right. Okay, so the thrust is equal to the mass loss rate times the exhaust velocity. Okay, mass loss rate is how fast you can throw them out the back, and the exhaust velocity is that fixed speed that you can throw them with, okay, out the back of the spaceship. Okay, so in equation form, we would write that as so the mass loss rate is the amount of mass that you're throwing out per unit time. So it's the change in the mass over the amount of time. Okay? So if a baseball was 0.5 kilogram and you throw it out once per second, then you're throwing out 0.5 kilogram per second. Okay? So the mass loss rate times the exhaust velocity. Okay. That's it. That's all you need to know about rockets. You throw mass out the back at some fixed rate. Okay? this is how much force is going to be pushing it to the right. Okay? Easy. Okay, let's do some demos of that, and then we will, I'll make the point about the misconceptions that people generally have for rockets. So this is a rocket. Your sink is a rocket. Okay? You turn on the faucet, and water starts being expelled. Okay? It starts being expelled at a fixed rate. It's got a velocity. Okay? So you might not realize that, but there is a force associated with that. It's the thrust. Okay, so let me turn this, start turning this up higher. Okay, this is a special faucet because it's free to rotate, okay, if it feels the thrust on this. So let me turn it up. Okay, you can see the what I'm increasing is the mass loss rate, the amount of mass per unit time that's being pushed out of this faucet. Okay, and you can see that's exerting a force on this lever arm, which is creating a torque in this system, so you can see it increasing. Okay. And so the higher the amount of mass that I'm expelled by turning this up, the more and more force that we create. I'm about to create a mess here. So it's creating a constant torque on the system. That, of course, is why your pipes creak when you turn the water on, right? So anytime you're expelling water out of the faucet, that's creating a force back on the faucet and all the pipes that it's being shot through. So your water system in your house is basically a big rocket ship. Okay? If you could just harness that to make your house move, that would be great. Okay, so if I turn this back down, cool. You can see that it's gone to I've turned off the thrust. Okay, back on. Cool. Okay, so let's do a little more dramatic example. Here is, okay, this is going to go across the entire room, so you probably need to pan out for this. Okay, here's our rocket ship. Okay. This is a little CO2 cartridge, so it's got compressed gas in there. So I am going to allow that gas to be expelled. So it's going to be pushing the gas out the back, creating the thrust, of course, which should hopefully, ow, I just punctured my finger, I think. Okay, that should be good. I'm just trying to build a little tension here. Yeah, rocket ship. Awesome. Yeah, I know. Isn't that cool? You guys can do that at home. Okay, let me do, I'll do one more of these, which is a same thing. So I got the gas cartridge inside this. This is our little rocket ship, but this one is tethered onto this pivot, so it's not going to go flying across the room. But at least we can zoom up on this one a little closer. There we go. Okay, so constant acceleration as it's expelling the mass out the back. We're getting the thrust. Oh, oops. It actually goes in there pretty far. Let's see. Oh, I see. I need to tighten this up. There we go. Okay. I need a better launching system here. It has no problem doing my finger. There we go. Okay. Constant thrust on that rocket. Constant thrust creating a torque, spinning this up faster and faster and faster. I need more CO2 in these cartridges, don't we? We need ultra high pressure. Okay, so rockets, pretty easy. We made it sound pretty easy. Okay? For some reason, people have major misconceptions about rockets. So let me list the 4 major misconceptions, and we will already see that we don't have these. Okay, the first and the primary misconception about rockets. Rockets do not push against the ground. Okay, you see those, you see videos of NASA launching its rockets, right? You got the gas and the fire that's being expelled down the bottom. And for some reason, there's this perception that the rocket goes shooting off because the gas is pushing down against the ground. If the ground weren't there, the rocket wouldn't take off. Okay? Not at all. It doesn't care at all that the ground is there. It's just the action-reaction pair, right? Conservation of angular momentum. So, it's just the action-reaction of the thrust of the gas going backwards against the rocket, which is accelerated forwards. So it does not care at all whether the ground is there. The second is that rockets can move faster than their exhaust speed. Okay, you can expel gas out of the back at some fixed exhaust velocity, okay? And intuitively, people, until they learn about conservation of momentum, just imagine that that velocity is the same as the fastest that the rocket can go. The rocket can go up to the exhaust speed of the gas, and then that's reaching the limit of it. Okay? Absolutely not true. We know from conservation of angular momentum that regardless of what speed you throw this mass out the back, that as long as you're throwing it in one direction, it's going to be creating an extra force that's pushing this to the right. So when rockets get going fast enough, even though they're expelling gas out the back, that gas is still actually moving in the same direction that the rocket's moving, right? But it's moving slower, and the fact that it's moving slower than the rocket means that it had to transfer some of its linear momentum to the rocket to move it forward. Right? So rockets can absolutely move faster than the exhaust speed of the gas. Okay? It's just simple conservation of linear momentum. Okay, the third one, this isn't actually such a misconception, but it's just something that people don't really always realize. Third is that rockets must expel a very large fraction of their mass. Okay, let's give an example of the space shuttle. We won't see any more space shuttle launches. We'll have to come up with a new rocket example, but until SpaceX gets their act together, let's give the example of the space shuttle. Okay? So the space shuttle itself weighs 55, wow, a lot of feedback there. Can you control that way? Okay. The shuttle itself weighs 55 tons. Okay. The amount of fuel that it expels to get up to orbit is considerably larger. The fuel to orbit that it expels is 2,000 tons. Okay. So it has to expel about 40 times the weight of the space shuttle in order to get itself up into orbit. So a huge amount of mass has to be expelled in order to get the speed up on the rocket. Rockets are not efficient systems at all. And then the last one is also more just information. Because of this inefficiency in rocket designs, how much mass they have to expel, the rockets are usually built in stages. Stages to discard storage mass. Okay, what I mean by that is, well, you see that already in the space shuttle, but let me draw a simpler picture from that. So, fuel stage number 1. Fuel stage number 2, and here is our actual little rocket on the top. I drew this sideways because I was running out of room, but imagine that vertical. Okay, so the way rockets are usually built is in multiple stages. Okay? So the first one, it will fire off that first stage, and it will go accelerating up into the air, okay, until that fuel is all used up. And at that point, you're basically accelerating the mass of this whole big storage container, which you don't actually need because you really just want to get this little rocket up into space, okay? Not all the storage mass. So they will at that point throw that back section off. It's usually an explosion that makes that kick off to the back, okay? And then they'll light this stage, okay? And then it'll keep accelerating with a much smaller mass, okay? Until that fuel's used up, okay? And then they'll break that, and then the rocket will accelerate it off. Okay? So they can have multiple stages, but that's why the space shuttle has the big, the solid rocket boosters, the big liquid tanks. Okay, so they're all made so they can expel that extra mass, okay, as they use it up for storage. Okay. That is all about rockets. Any questions about rockets? See, we're just sort of whipping through these final topics. Classical mechanics looks exciting. Maybe moving on. Yes?
What if the rocket didn't start at rest?
Right, so if it starts, so I drew this starting at rest just to simplify the situation, right? But let's say it starts off with some initial velocity to the right. So the question is, what happens if the rocket doesn't start at rest, but it's got some initial velocity, right? So nothing. Absolutely same thing happens, right? So you throw a mass out the back, or you expel the fuel out the back. So you're transferring momentum to it in the left-hand direction, which means that it's going to keep accelerating to the right. So exactly the same situation. So if you want to slow it down, you will turn it around and expel the gas out the other side, right? So it decelerates it. Yeah, good question. Any other questions? Yeah. Can you say that one more time?
So is it a fixed acceleration for the rocket?
I see. So, right. So the question is if it's a fixed acceleration for the rocket. So as long as the, so if the exhaust speed is not changing, so if you can throw that gas out at a fixed speed, which most rockets do because they have a, there's usually some burning, right? And it's the burning which is actually throwing the gas out the back. So that is usually a fixed for the rockets. And then it's just a matter of how much mass you're expelling at a given time. So, and it's mostly a matter, I think, of just practicality, how fast the rockets can go. So how fast they can accelerate, because they're trying to accelerate them as quickly as possible to get them into orbit. But they don't want to actually kill any astronauts on the rockets. So there's a, I forget how much acceleration the human body can take, but it's several G's before, people start passing out. And so, so there is a fixed amount of, mass loss rate that they control with these, and it's primarily, to make it a survivable environment for whatever they're trying to accelerate up into space. So, does that answer your question? Okay, good. Yeah.
Why are there a lot of countries that aren't as successful as the U.S., I guess, in regards to the rocket program?
Creating rockets. So that's a good question. So why aren't there a lot of countries that aren't as successful as the U.S. in creating rockets? Well, and there's certainly a lot of countries that are trying, right? So China's been growing its rocket program quite a bit in the last decade, and India has, as well as Brazil. That is a really complicated question. So And I would say that it has almost 100% to do with politics and less to do with technology. I mean, there is, we've all seen lots of videos of, rockets exploding. There is certainly a lot of safety factors you have to take into account. And so the technical challenges are not negligible, but it's really a question whether the countries have resources and national priorities in order to develop these programs. And fortunately or unfortunately, these rockets that throw stuff into space are often pretty closely tied to rockets that can hurl weapons, explosives from one country to another. And so, for example, the U.S. has a quite large space exploration program. I would say that was not driven 100% by our desire to explore space, but maybe partly, but partly our desire to build the technologies for defensive systems as well. So yeah, good question. It's not, in this case, I would say it's not all technical, so it's probably political, whether you just want to invest the resources in that or not. But a lot of other countries are building their space programs, so I think, especially over the next couple decades, I think you'll see a lot more international collaboration and a lot more commercial launches coming from India and China and places like that. So, yeah, good question. Yeah. If the exhaust velocity is a constant, is not a constant. If it decelerates, well, my guess is in the real world it does decelerate. So that it gets lower. So this is definitely a sort of a simplified picture. In which case, computer control is great. You can control as you're running out of fuel in one of these systems, right? You can start pumping up the mass loss rate in order to keep the acceleration whatever you need it to be. But certainly if the exhaust velocity starts to drop, so you start getting very tired throwing these baseballs out the back, then the amount of acceleration you're going to get out of that is certainly going to start dropping as well. Good question. Okay, good. Yeah, last question on this.
Earlier you mentioned the example of a bicycle having dynamic stability with rotating wheels.
Uh-huh.
The linear momentum of the rocket, does that provide any kind of dynamic stability?
So the question is, so we had talked about the rotating reels, for the people you couldn't hear, on the bicycle, providing dynamic stability for the bicycle. And the question was whether the rocket thrust provides a form of linear stability, stability because it's got linear momentum. So that is a really good question. I think I summarized it, but can I answer that? It certainly has I guess the question is stability against what?
The reason I asked the question is because you mentioned, everybody's seen pictures of rockets exploding.
Mm-hmm.
When I've seen the pictures of the first test, it's always when the rocket doesn't have much momentum. It's just lifted off the pad and it tips over.
And it tips over, right. So you're talking about, right. That's a good point. So his point is that, usually when rockets fail, they fail on a launch pad, unfortunately. So which you'll see them starting up, and then you'll see them come back and crash down or fall over, whatever. Yeah?
A rocket isn't necessarily any more stable than it's going past if you need aerodynamic stability, or if you need pins or some kind of gyroscopic pulses that keep it moving straight up.
Right. So his point is whether the momentum adds aerodynamic stability in the atmosphere, right? Or gyroscopic. These are all really great questions. I don't know if I can answer that. So, you stumped me. It's certainly rockets are designed aerodynamically to work in the atmosphere, right? So, right. So once you pick up a linear momentum in this direction, then rockets usually have these wings on them or the fins on them, And the airflow over those will certainly stabilize. It's meant to stabilize the rocket in order to keep it from, starting to flip or spin out of control. So there is definitely aerodynamic stability you get from having momentum in this direction, which is basically these wings start kicking in. I don't think that affects the launch itself, though. The launch is really a question of whether they've just perfected that initial thrust. So basically, what happens at launch is that you need to have enough thrust in order to overcome the weight of the rocket. And so given the mass loss rate and the exhaust velocity, that has to be high enough to overcome the weight. And so if you've got that controlled, then it should go up no matter what. It's not really a question of linear momentum. But if you don't have that control and the weight overcomes that, then it's going to be disastrous. So, but certainly once it picks up linear momentum, then these wings definitely start kicking in to provide stability for it going up through the atmosphere. Completely useless in space, of course, where there's no air. But they would definitely be designed to provide stability when it is moving in the direction that it should be moving. So, yeah, that's a great question. I might have to think about that one some more to think if there's any other effects there. Okay, so let's move on from rockets. Let's see what time. We got 15 minutes. Okay. We are just going to summarize a little bit Newton's laws of gravity. Okay. Let's see. Let me start. I'll start over here. Okay, gravitation. We already talked a little bit about Newton's laws of gravity when we talked about the apple falling on Newton's head and his realization that the apple was falling because of gravity, and the fact that it was falling from the top of the tree meant that gravity was acting over very long distances. And then that naturally led him to start thinking about whether gravity was acting on the moon, on the sun, on the earth, on the planets in the solar system. Okay? And that's where he came up with his law of gravities. But the story actually starts earlier. And it started in the late 1500s with a Danish astronomer whose name is Tycho Brahe. Okay, Tycho Brahe was basically an astronomer in the late 1500s, and what he did was he created a huge database. So he was obsessed with following the motions of the planets and the moon and the sun all through the sky, and he basically just cataloged that every night for many, many years. And he came up with a huge database of just the motion of the planets in the sky. As far as I know, he didn't do anything with that. He just cataloged it, okay? So he was a good database creator from the 1500s. So he would have been a good source for Google information these days. Okay, after he died, all of his data was available, and it was picked up by another astronomer, this time a German astronomer, who was a little bit more mathematically oriented. And that was Johannes Kepler. So Kepler took all this data that Brahe had collected about the motions of the planets, and he analyzed it in great detail mathematically. And so from studying that data that Brahe had collected for years, Kepler came up with 3 empirical laws. Of planetary motion. So this is how the planets move in the solar system around the sun. They're empirical because he deduced those from the data. He was able to figure out the motion of the planets from the data, but he couldn't explain them. He could just tell you what they were. Okay? And he found these 3 interesting trends in the data. Let's summarize those really quickly. Basically, the story goes that once Newton figured out his laws of motion, he also could go back to Kepler's 3 laws of planetary motion, and from those he could deduce the law of gravity. Okay? And the reason is because that he had mechanics on his side. He assumed that it was gravity that was causing the planets to move in their orbits. Okay? And then he could deduce how gravity must be acting from the fact that the laws that Kepler had found already existed. Okay, so the first one of Kepler's laws is that all planets move in elliptical orbits. Around the sun. Uh-huh. Oh, thank you. Elliptical, not elliptical. Elliptical orbits around the sun. Okay? So, technically, the sun is at one focus of that. If that doesn't make sense to you, don't worry about it. Let me just draw the picture. Okay? So here is the sun. Okay? Here is a planet, and it could be Earth, Mars, Jupiter. All the planets move in ellipses around the sun. Okay? Ellipse is just a squash circle. Okay? Some of them are very circular. So these are, in fact, almost all the planets are have very circular orbits. Okay? But technically, when you look at them closely, they're all a little bit squashed into ellipses. Okay, so Newton could explain that very easily. So this is just centripetal motion. Okay, and the effect, what that means for gravity is that gravity is providing a central force. Okay. Gravity was always directed towards the sun in this case. All the gravity, the sun was always pulling the planets directly towards it. So the gravitational force which is really just the weight, okay, of the planets was always directed towards the sun. Okay, the second law that he saw is a little bit more subtle, but it has a really simple explanation. So his second empirical law said that a line joining a planet to the sun sweeps out equal areas in equal times. Let me write that down and draw it. So a line connecting, or a line joining any planet to the sun sweeps out equal areas in equal times. Okay, this is kind of an obscure law. Okay, let me draw what that means, and then we will talk about physical interpretation of that. So here is our planet, and I'm drawing a very large elliptical orbit here. Okay, and let's imagine we're going to look at the orbit of that planet for 1 month. Okay, so here is the line joining the planet to the sun. And let's follow that planet for 1 month. So let's, for example, say it's the Earth. 1 month later, it's moved here. Here is the line connecting it to the sun. So let's say this is 1 month, just to give a specific amount of time. Okay, so this has swept out an area there, okay, which is what Kepler was talking about in his law. Okay. If we go to a later time when the planet is much closer to the sun, here is the line connecting the planet to the sun. And if we go forward for 1 month, on this side, okay, then Kepler's law just says that if you look at it equal amounts of time, so for this case, 1 month, that this area is equal to this area. Okay? Sounds very extremely obscure mathematically, but let's just see conceptually what that means. Okay? Here the planet is much closer to the sun. In order for these areas to be the same, that means the planet over here must be moving faster in its orbit. Okay. And over here, where it's further away, for that area to be equal to that area, it must move slower. So all Kepler's second law is telling us is that as a planet gets closer to the sun, it moves faster, and as it moves away, it moves slower. Okay? We know what that is. Kepler had no idea what that was, but we know what that is. Any ideas? Remember our ice skater or our rotating chair, right? You pull in closer, the mass gets closer, the rotational mass drops, okay, so the rotational speed picks up. This is just conservation of angular momentum. As the mass of the planet gets closer to the sun, its rotational mass decreases. Okay? So its rotational velocity, or its orbital velocity, has to pick up in order to compensate that, to conserve angular momentum. Okay, so third law. Oh, let's leave that there. Okay, Kepler's third law just said that the square of the orbital period so the orbital period is how long it takes a planet to go around the sun. So for the Earth, that's 1 year. The square of the orbital period for any planet is proportional to the cube of its orbital radius. So proportional to the cube of how far away it is from the sun. Okay, so let's write down some numbers for these. And you can see, for example, for the Earth, its period, its orbital period is just 1 year. Okay? Its distance from the sun is something we call let's call that R. We call it 1 astronomical unit. That's 150 million kilometers. Okay? That's our distance. Okay? For Mars, its period is 1.88 years. Its average distance from the sun is 1.52 times as far. Okay. And I won't make a big list of these, but let me just tell you the upshot is that if you look at the ratio of the orbital period squared to the distance cubed of the object from the sun, that is equal to a constant for all the planets. Same for the Earth, for the Mars, for Jupiter, for Venus. Okay? Kepler had no idea what this was. Okay? A lot of people picked this up as some sort of mystical occurrence, that this was just some coincidence. Okay? Newton explained this as the gravity falls off as 1 over distance squared. Okay, so that's where we will stop for today. This is a very easy explanation for why the period and the radius scale, okay? And that's in your book, but we'll probably talk about that very briefly at the beginning of next lecture.